Right. Hi. Welcome to my session on GitLab architecture. This is going to be a fairly introductory session. I don't think I will cover things like high availability components. So probably we'll not be talking about things like Postgres clusters or Redis clusters. We'll just mainly be focusing on how the individual services that make up GitLab, that make up an GitLab environment work and how they kind of work together. I wouldn't be covering all the components as well, just the core components. So I probably will not be talking about things like GitLab pages or registry or some of the other ancillary services that we do have. So before I really get into it, I just wanted to say that my explanations are actually based on my experience as a developer of Rails applications and deploying Rails applications. I have never taken a computer science course of any sort. So in many cases, my explanations will be based on just the way I kind of see things. They may not actually be technically accurate explanations. So my suggestion is do your own reading. And if anyone does want to chime in with a more technically accurate explanation, please feel free to do so. This hopefully will be a bit more interactive. My other thing I wanted to say is that I hope that everyone on this call and everyone who also watches this call async will actually build upon this and create more training material and more in-depth material that people can actually use. My hope is that this recording doesn't become the resource for understanding GitLab architecture, but it might be a good starting off point. So with that, let me get started. I'll share my screen. Okay. But before I go on, does anyone have any questions or any general thoughts they might have? Which is a bit of a strange question to ask, I guess, because it's a bit vague, but yeah. No? Okay. Well, let's see how things go then. So I think the very first thing that we need to know about when we talk about GitLab is, of course, Rails, because the entirety of GitLab is essentially built around Rails. Rails on its own is basically just it is basically just a framework written in Ruby that allows you to serve web requests. So we'll start with Rails, and I'll just draw a heart here as well. To show you that, just to say that, this is the core of the application. I want this color. Right. So Rails itself, it's actually just the framework. It is sort of like it is a framework that takes on web requests, and gives a response. But on its own, it's actually not the web server. The web server itself is actually Puma in current GitLab environments. We used to use Unicorn, but now we use Puma. So one thing to know about Puma is that Puma is actually what they call a rec server. So in Ruby, there is this web request framework called rec as well. So that's RACK. So what rec does is that it actually provides a standardized way to actually take on a request, transform it in some way, and then pass it on to the Nginx chain. So Rails itself, as you might guess, is actually a rec app. And if you have looked at some tickets before where we do talk about request throttling in particular, you might have heard of this
rec timeout?
Yes, rec timeout is one of them, and then rec attack is the other one. So how it actually works is that there is actually a rec app. Let's use rec timeout since you mentioned it. Called rec timeout. So this actually sits in front of the stack. And then in between, you have other middleware as well. So, I mean, we call it middleware because we basically sit in the middle. So what happens is that essentially a web request comes in, Puma would serve it to basically the first rack in the rack stack, and then it basically goes down, and then it finally goes to Rails, and then you get a response. So generally, that's, I mean, it probably isn't the best explanation, but that's how it works. That's how this works. This is also why if rack timeout or rack attack, which we use for rate trotting, if they actually reject a web request, this is why it never shows up in Rails, because essentially execution stops before it even gets to Rails. So this is kind of how Puma itself works. Any questions about this so far?
Sorry, I have one, Wei Ming.
Sure.
You said that Rack is this Ruby app that's like a middleware between Puma and Rails. And if there's some sort of a rejection of the request prior to getting to Rails, you know, that'll happen outside of Rails. But if Rack's a Ruby app, is that, is that using the same like Ruby runtime, or is it different? Is it separate?
I don't know the answer to that actually. So all of Rack apps are all middleware. And in fact, Rails itself is a Rack app as well. So it's just that Rails happens to sit at the very bottom of that stack. If that makes sense. So Rack timeout sits on top of that. Another good example of a Rack app, which I think you might be familiar with, but you might not have realized that it actually is a Rack app. Rack app is actually OmniAuth. So we use OmniAuth to provide authentication processing for different providers, such as GitHub, I think Google as well, and SAML and a bunch of other stuff. So how it actually works in this case is that it actually receives the authentication callback from these external providers. It then kind of takes the information that we need, which is generally the authentication token and the username, I think, and adds it to the request environment variable. So this is how Rails kind of knows in a standardized form how to kind of interact with those things. So sorry, I think that was a bit of digression, but does it help you to understand kind of how it works?
Yes, that was awesome. Thank you.
Okay. But yes, I don't actually know if it's the same Ruby environment. I think it is because I think I think it's the same Ruby execution environment. But yeah, I don't know the answer to that one, to be honest. Let's erase this first. Yep. Any other questions about Rack? Particular?
Where does it log?
You mean for the Rack applications?
Yeah.
That are not Rails. I'm not sure actually. I do know that for Rack attack, when a request is rejected, I think we actually log that in the authentication log.
Okay.
But yeah, in general, if there's any logging to be done, it will have to be done intentionally by the GitLab developers. So I don't think we actually have it. So this is why they don't show up in the Rails logs, but the requests do show up elsewhere. So for example, we'll talk about this a bit later on, but in Nginx, they definitely show up. In Workhorse, they show up as well, because those are just reverse proxies and all requests will go through them. So they will try to forward it to Puma. And then if it kind of, disappears and it doesn't appear in the Rails application log, that probably means that it was rejected somewhere between the reverse proxies and Rails itself. So there will be traces of those requests that might be rejected by a Rack app that is in the chain before Rails. But yes, it will not actually appear in the production or production JSON logs.
Okay.
I was trying to see if it's fair to say that Puma as a Rack app is a way to translate web requests, which goes through the web server Nginx, into the Rails, as in the Ruby components of it. Is that, can you think about it in that way, or is that not the way to think about it?
I actually don't know the technical details of that, but my understanding is that rack kind of takes a incoming HTTP request, right, and then transform it into sort of like a standardized format, so that any other person that wants to write a rack middleware or a rack app has a consistent interface that they can work with. So they don't have to worry about like, hey, if you're sending in this request, what are the headers that you're going to use. So it kind of takes all of that, and then it kind of transforms the request into something that is kind of like a standard interface, so that anyone that wants to write a rack app, they can do so without having to worry about, I have to think about so many other ways that you might actually end up having a HTTP request. It's kind of like XML. For people that have worked with XML. There is a standard for XML. Usually there is a documented standard in terms of what keys to use, what attributes to use. But of course, no one follows that. Everyone has their own XML standard, and that is a pain. So yes, one of the, I think you might have heard about this as well, but one of the big things about Rails and Ruby in general is convention over configuration. So we try to standardize everything so that people have a stable interface to work with. Yeah, so that's kind of part of it. Does that help?
Yeah, I think there is a section that you go through Nginx later as well. Maybe we can have further discussion there. That's
sure.
Yeah.
So there are a number of other things I wanted to talk about specific to Puma. So if you have spent some time looking at GitLab logs, you might have noticed that Puma workers tend to be killed after a while. And it's not, it's not like a few minutes. They're actually killed something like every 20 to 30 seconds. The reason why this happens is that we actually have a gem, which we use called Puma Worker Killer. So this actually prevents Puma from consuming too much memory. So we essentially kill Puma before it takes up too much memory. So I actually read up about this recently, and I have links as well to some references you can read in the document. So I used to think that the reason why we had to do this was that Rails applications or Ruby applications in general, they tend to leak memory over time. It turns out that my understanding is wrong. It turns out that actually Ruby does have a pretty good garbage collection process. It's just that for web applications like Rails, memory allocation happens when clients hit endpoints, and the frequency of of endpoints being hit in a web application is high enough that Ruby actually ends up allocating more memory than it frees up. So essentially, garbage collection happens slower than requests come in. So memory allocation increases over time. The reason why we want to kill Puma workers before they consume too much memory is because we want the memory consumption to be relatively I guess within a known range, because the amount of memory that a Puma worker takes up does affect the total number of workers you have. I mean, you can't exceed the total number of RAM on your system, for example. So that's one reason why you see that all the time. And it's not a sign of the Puma itself being unhealthy. If it happens something like every 20 seconds to 30 seconds, or even 40 to 50 seconds, that's actually fine. But if you see it happen too often, like 5 seconds or 6 seconds, that's probably a sign that too little memory is allocated to each Puma worker. So yeah, any questions about that?
You mentioned about that is actually scheduled to be restarted on I think a daily basis. The worker killer. Did you mention that just now?
No.
Oh,
that does it. So what happens?
It does, yeah.
Yeah, what I mentioned was that the Puma Worker Killer basically detects when each Puma worker is consuming a memory beyond the limits, then it kills that worker, and then basically the worker will restart on its own.
So that's what I was about to add. Just there was one function of it. So having Puma Worker being killed sounds bad, but it's not necessarily bad from the stability standpoint, because the whole point of having this is to actually maintain the memory, right? And I think, yeah, there was another thing about this. This was the worker kill actually configured to, we call it the word recycle. We get recycled on a daily basis. That's just part of the default configuration. And I think, yeah, basically it's the same thing, just to maintain the memory usage of the Rails. Anyway, I thought it was just something that if you see that it got restarted, it doesn't mean it's necessarily bad. I think the frequency causes issues. Yeah.
I did not know they actually restarted it on a daily basis by policy. So one other thing that I should mention is that when I say the Puma worker gets killed, it always gets restarted, because if say if we define in the GitLab RB file, we always want to have 6 workers, for example, there will always be 6 workers. So even if we kill one, the Puma master process essentially will try to restart it such that there will be 6 processes. I don't think it's really processes, sorry, 6 workers. So yeah. Any other questions about Puma Worker Killer?
Is there logic to ensure that Puma it doesn't get killed in the middle of a request?
No, there isn't. So it is very possible that Puma Worker can get killed in the middle of the request. I've seen it happen before, not in GitLab actually, but in some of the other Rails applications that I've developed. So yeah, when that happens, all you see is I think a 502 error, if I'm not wrong, or 500 error, 502 error, 500.
Yeah.
One of the errors anyway.
I've seen that. I've had a couple of tickets involved where Puma Worker Killer was killing the Puma workers in the middle of requests, and the users were getting 502s, but sometimes depending on the request, they may not receive that, but they might maybe see request fail or some other functionality not working as expected. Yeah, and usually in those times we would, increase the worker per worker memory to avoid that from happening. But yeah, you were saying, Wei Meng, that it being killed frequently isn't necessarily a bad thing, but if that's happening in the middle of requests, that can cause instability. Is that right?
Yes, that's right. So when I say killing too frequently, I mentioned the number of 20 to 30 seconds being okay. So that is just a general guideline. The real test of whether your workers are being killed too frequently is actually yes. Are too many requests being cut off in the middle of something happening. So this is actually a statistical game basically, because if your workers are restarting too frequently, what will happen is that you get a whole bunch of requests that there'll be more requests essentially that get cut off mid-flight, and then that creates a poor user experience. So 20 to 30 seconds is probably a good guideline as to what's okay. But yes, if you do hear customers reporting that there are mysterious 500s or 502s all the time, yeah, that probably means that there's too little memory allocated to each Puma worker, and they're restarting too frequently, causing there to be too many opportunities where connections get cut off mid-flight. So yes, that is the better way to look at it.
I'm trying to follow up with Kenneth's question earlier. You were asking about whether there is the graceful termination of connection. Was that any particular reason you're wondering about that? I'm just curious.
Are you asking me?
Yeah, I'm just curious about like why you asked that question, because yeah, anyway, I have some thoughts on it, but I'm curious.
No, I was just mainly curious to know if there was logic to make sure that a request finishes and make sure that Puma is doing nothing before it gets killed or not. Or if it just, it's using so much memory now, it's going to get killed.
Yeah. So this is the thing. My understanding of part of this is also because if the code itself actually have some runaway process that I don't know, not garbage collected properly, this Rails timeout actually guards against that. But that's my understanding of why it doesn't actually have a graceful termination. That's my understanding of that, but that's probably something that I'm not fully clear about too.
I'm not fully clear about it as well, but I think I did read somewhere that it is extremely difficult for Ruby applications to know introspectively how much memory is actually consuming. So the way we queue Puma workers is actually a separate outside of Rails sort of process. So it doesn't actually know what Rails is doing. It just sees that the Puma worker is beyond the range of acceptable memory usage, and it just queues it, regardless of what's going on with that worker process at that point in time. So again, take this with a pinch of salt. This is somewhere where I'm not super familiar with, but yeah, I just know that that there is no graceful shutdown of Puma when it exceeds its memory when Worker Killer is involved. It just kills it rather impolitely, actually. Cool.
Okay, thank you.
I just want to touch on some of the scaling triggers that you might see for Puma before we move on to the rest of the GitLab components. So the scaling triggers for Puma are basically CPU. You need CPU to run the workers. It's actually less than Unicorn. If you're familiar with Unicorn, Unicorn is basically one Unicorn worker per vCPU. Whereas I think Puma is evented, so there's a bit more play there. But CPUs are still something you might want to think about. The other scaling trigger that we have is RAM. If we have 4 workers taking up, I think 1.2 gigs of RAM each, and you only have 4 gigs of RAM, yeah, that's not going to fly. So the other scaling trigger is RAM. If you're running out of memory to run more workers, then yes, you need more RAM. Hang on, just write this down.
I was about to say also reduce the number of workers so it uses less RAM. But anyway.
Yes, you could do that. So if you want to maintain the amount of RAM, then you need more machines. But I think that's a bit out of scope of this environment session. There's also one other scaling trigger to think about, although it's more of a performance problem than a real scaling trigger. In a very extreme cases, you can actually run out of file descriptors for Rails applications. The reason behind this is that Rails and Ruby, Rails in particular, is dynamically compiled. So essentially, whenever you run a Rails application, it basically opens tons and tons and tons of files. So in very rare and extreme cases, we have seen this a few times before. Customers actually report that the underlying OS reports that it can no longer open new files and it just refuses to do anything. So that's something to think about as well in case you do encounter this mysterious thing where mysterious errors are happening, but you don't really know why. It could be worth checking that. So yeah.
You can also configure, apart from the number of workers and the number of amount of RAM per worker to consume, is the threads per worker. And a lot of the time, you should keep that default. But Harsh and I had an interesting problem where our customers, Puma, it wasn't starting up. It just was taking too much time and it timed out. And it turned out that they had set the thread count too high, and it was just taking way too long to stop and start. So I think it was like 16 or something, and we tested all the different numbers from 1 to 16, and once it got beyond 14 or 15, yeah, the time it took for the amount of workers in the threads to be destroyed and created, it just was way too long. I'm not sure when they would want to customize the threads, but yeah.
Yep. Thank you for that, Mike. So I will move along now into the more interesting part about this, and we'll talk actually about the one key reason why we have more than just Puma serving up GitLab. So I think many of you might be aware that there is a 60-second request timeout on all of Puma requests. So here's where I have a question. Do you know why we have that 60-second timeout?
I thought it was just for hang processes. So there is if there is a request and I don't know, the request hung for some reason, you wanted to like stop that.
Yes,
But maybe that's a simplistic explanation of it. I don't know.
that is actually part of the explanation. But yes, why do you want to stop hung requests?
So if the request hung and the Puma keep getting requests again and again, and all of them got hung, basically the whole Puma pops up, right? That's my understanding. Anyway, that's my understanding why you want to cut it off in 6 seconds, because then the request stacked up and all of them connecting, trying to process something, but it's hung. So all the workers and all the threads are processing things that hung, hence it fails.
Yeah, that's exactly the reason why we want to have a 60-second timeout per request. So if you have many, actually you don't need that many at all. We'll talk about this when we talk about Gitaly, which is interesting. But if we have 2 or 3 requests that take, let's say, 2 minutes each, and you have 4 of those, and you only have 4 workers that are serving requests, essentially you have a situation where you have encountered worker exhaustion. There no longer is any more workers that are available to serve incoming requests. So you start to get 502s. So the reason why we have a 60-second timeout, I'm not sure why exactly it's 60 seconds, but it seems to be a good middle ground between allowing the web server to run and process slightly longer running requests versus not having so many extremely long requests that you end up with a situation where there's a high chance that all of the workers will be busy at the same time. So yes, so this is why I believe in our documentation in the past, we used to put in things like, you can actually increase the timeout, but be careful. They don't actually tell you why you have to be careful. So this is the reason why. You have to be aware that if too many long-running requests happen at the same time, you could end up with a situation where there are no longer any workers left to serve requests. And if a customer is saying that the timeout is too short, it does suggest that they have too many long-running requests anyway. So they might be digging the hole deeper for themselves.
If you increase the Puma timeout, you would also have to increase the Nginx timeout, because that's defaulting to 60 seconds also.
Is it?
Well, I don't know what we set it to, but the Nginx default timeout is 60.
That makes sense. I mean, I don't know if that's the case, but if it is the case, then yes, we would have to increase the timeout across the entire chain. Yeah, there are also other timeouts with other components, but yeah, we'll get into that. But yes, any other questions about the timeout that we have on Puma request? Okay, so I specifically want to talk about the timeout because this is actually the key reason why we have so many other components. So I guess the next question to ask, right, is if we have a 60-second timeout on Puma request, then how do we actually run processes or run transformations that actually take more than 60 seconds? And anyone know the answer to that?
We don't run it in Puma.
Yes, we don't.
Sidekiq?
Yeah, exactly. So we run in Sidekiq. So this is exactly why we are Sidekiq. So the whole purpose of Sidekiq is to actually run jobs in the background. Sidekiq itself is actually a Rails server as well, sort of. It runs the exact same copy of Rails that the Puma or GitLab runs on. It's just that it does it expressively for what do you call it? Running background jobs. So yes. There from a web development perspective, there are actually a few reasons you want to run Sidekiq beyond just, having beyond just jobs that might take longer than 60 seconds. So a good example is when you actually need to async something where it doesn't make sense to have it block a synchronous transaction. So a good example is, say if you create a comment in a support team meta issue, and on that support team meta issue, there are, I don't know, 30 other support engineers who have also commented. Can you imagine if you kind of post a comment and then you have to wait for the SMTP server to send 30 emails to notify everyone? It'll take forever. So what happens is that we will just actually send the comment first, and then we'll send a background job to Sidekiq, or 30 background jobs to Sidekiq actually to send those emails. Something else you might have seen with background jobs is also with payment processing. You might have encountered before where your order actually is confirmed, and then sometime later you get a notification saying that your payment method has failed. That's because some e-commerce platforms, they essentially want your business, so they confirm your order first, and then they process your payment in the background, because sometimes payment processing can take up to 2 minutes, if I'm not wrong, to clear. So yes, some e-commerce websites also do that, where they actually process your payment in the background, and they tell you it has succeeded when it actually has not. So that's another thing. Cool. There are timeouts with Sidekiq as well, but they are significantly longer than Puma. I think the Sidekiq timeout by default is 3 hours or something like that. I'm not too sure. But yeah. That's actually pretty much it for Sidekiq. There's not much to talk here. However, we will talk about how Puma, or how Rails itself, actually sends jobs to Sidekiq. So yes, how do jobs get sent from Puma, or rather the web Rails, to the Sidekiq Rails? Does anyone know the answer to that?
There's usually a worker class that it calls. Is that right?
Yes, that's right. There is a worker class, and there might be arguments as well, right? So I don't know, argument 1, argument 2, argument 3. Let's just do this. Cool. Yes, so it has a worker class that it kind of calls, or at least Sidekiq calls it. But how does it know when to call it?
This is like the async something. Is that related to that? The async one?
Yes. So I mean, if you have jobs to process in the background, you also have a queue of jobs, right? So I guess my question is where is that queue of jobs stored?
I feel like the hint is your next section, Redis.
Yeah, if you kind of read the document, yes, you can actually tell the answers to my questions. But yes, it's Redis. So we store, basically the queue is stored in Redis. And I think Mike, you're very perceptive. You actually said, T-Mike, that is, there is a worker class and then you have arguments. So in Redis, oh, my handwriting is terrible. Let me fix that. And again, I don't know if I'm using the correct flowchart symbols for this. Forgive me if I'm mangling it. But yes, so the queue, the background queue for Sidekiq, it's actually stored in Redis. So quick introduction to Redis. Redis is a key value store that is very, 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 very fast. And the reason why it's so fast is that the entire of its working memory is stored in RAM, essentially. So the scaling trigger for Redis is just the amount of RAM you have available to Redis. If you are, I would be very surprised if you run out of RAM with Redis, unless you are provisioning some very set amount like 1 gig or less to Redis. But yeah, it scales to as much RAM available as it does have. So how the web Rails actually sends jobs to the Sidekiq Rails is that it actually does this. It essentially sends a request to Redis saying that, I want to store this data, essentially, this one. So I want to send the worker class with the arguments into one of the lists, basically. So one more thing is that Redis stores keys, values in lists. So each list essentially represents a queue in Sidekiq. So by storing the worker class and the arguments, Sidekiq can then poll Redis, and then it knows which class to run and which arguments to use. So that's exactly how it works. Cool. Any questions about this? Okay, cool. So with Redis, we have a very, very fast store of information. It's all in memory. Things happen very quickly. You send a request to it, it just gives you back the value immediately because it's all stored in memory. What else is that good for? Like what is a very fast in-memory storage of information good for in context of a web application?
A cache.
Yes, exactly. So so remember the 60-second timeout per request. This is a key optimization we need to always plan against. We want web requests to be as fast as we can so that we can serve more requests per worker. So exactly, Redis is used as a cache. So basically, if we have something that requires a lot of processing time to get a result of, what we do is we store it in Redis as a cache. Throughout the Rails code base in GitLab, you might see this term memoization. Yes, this is actually basically taking a result, storing it in cache so that the next time you access it, you no longer have to run the calculations anymore. You just get the result directly. Some common things that we store in cache are not just things that require a lot of processing, but also things that are very commonly retrieved, and it's much faster to retrieve this from Redis than it is from the database. So one common example for this is actually application settings in GitLab. So if we had to pull application settings from the database all the time, which is pretty much every single request, they'll be very slow. So we get it from Redis instead, and we put a copy in Redis. Cool. Any questions about this so far?
I just recently found out, this is probably a bit more kind of HA, but not really either. So I started recently find out that we can separate Redis cache and Redis persistent. So I'm assuming the cache is that, right? The settings and so on, and the persistent is the list for Sidekiq.
I'm actually not too sure about that.
Okay.
What I know about
Mhm.
I was going to say what I know about Redis is that Redis stores everything in memory, but it still needs a way to persist this between events where you restart your server or you lose power to your server. So as far as I know, in the context of Redis, persistence means that I can't remember how often it is, but every so often it does actually persist all of its in-memory values to the disk, so that the next time Redis reboots, you can actually repopulate the what's in memory. So I'm not sure actually what you mean by we can separate the Redis persistence from the Redis values in memory.
I literally just find out like half an hour before this call that we can actually separate Redis cache and Redis persistence, especially in the 10K architecture above. So that's why I was like, wait, this is a new thing for me. So I've started to kind of like think about it in a different way, because I always thought Redis is a very, it's storing memory, right? So like I always assume that all the content in it is very ephemeral, like it can just like disappear. But obviously with, well, not obvious, I guess, but with the way, how you interact with Sidekiq, it's like, well, all these lists about things that hasn't been processed need to be stored somewhere, because like, yeah, they need to be restarted and stuff. And yeah, I just realized that of course there's a persistent aspect of it. And yeah, anyway, I started thinking about this just like recently. So anyway, sorry, just my own personal questions.
No worries. That actually gives me something to look more into as well. Because there are many different ways to do Redis. Like it stores things in lists. So in theory, you could have multiple Redises, each with its own different set of lists. And this is kind of what we do with Sidekiq as well. If you kind of want different workers to process different queues, we have them in separate lists. But yeah, I won't go over that. But yes, there are many ways to scale Redis, which I am not really familiar with. So I'll look it up. Thanks, Andrew.
Just for my understanding, so for the asynchronous jobs that Rails initiates, so does Redis store which jobs are needing to be run, like the queues, but Sidekiq actually does the execution of that in its own little Rails environment? Is that correct?
Yes, that's right. So in this flow here, what happens is that the web Rails will say, okay, based off this request, I want to run this worker class with these arguments. So essentially it stores these arguments into Redis, and then later on, Sidekiq, when a Sidekiq worker is free, it will pull Redis for the next job in the queue essentially, and it sees worker class. And these are the arguments. So it has the same copy of Rails that the web Rails does. So it will have this worker class as well. So it just runs the worker class with the arguments. So yeah, that is kind of like the flow conceptually anyway of how it works. So
that's awesome.
Yeah,
thank you
your
very
understanding
much.
is correct. Cool. No worries. So the next thing I'll probably talk about is Postgres. So, all web applications do need a persistent store. In our case, we use Postgres as our database, our relational database. So, Postgres, I think this is, yeah. So, for Postgres, there isn't really much to talk about for Postgres in terms of the service on its own. But I really want to talk about how the connection between Postgres and Rails works. And we'll touch a bit about high availability as well, just a little bit. But briefly about Postgres. Postgres actually works very similar to, actually, I don't know if it's similar, but how Postgres works is that Postgres will have a master process, and it actually creates a fork of itself whenever it needs to serve a new request. So, if you have one database request come in, you have one process. If a second one comes in, it will fork itself and creates an entirely new Postgres process to serve the second incoming database connection. So this is actually a really expensive process, as you might imagine, which is why we have this thing called connection pooling. So I'll talk about this really briefly here. So let's do it this way. So Rails, and then we have Postgres here. Right, so Rails has this thing called a built-in connection pooler. And connection pooling is actually, it's not unique to Rails. It's actually a basic database sort of thing for forking databases anyway. So you have a pool, and inside the pool, you have basically multiple connections. So the idea behind this pool is that, and keep in mind that in order to serve new requests, Postgres will always fork itself, and that forking to kind of basically start up a new Postgres process is a very expensive one. So the reason why we have a pool with multiple connections in that pool, hence a connection pool, is that once one database connection is done, it doesn't actually close that connection. It maintains the connection in a pool so that if there's a second connection, it can actually reuse an existing connection. So you don't have to keep forking Postgres, or rather Postgres doesn't have to keep forking itself in order to serve new database requests. So this is basically a performance optimization technique. And this is why you might hear about things like database pooling or connection pooling. So this is a useful concept to understand that Rails actually does it natively. So Sidekiq does it, Puma does it, or rather Rails does it more accurately. Any questions about connection pooling and why we have it?
So there is a connection pool per forked process. Is that right?
So how this normally works is that you define like you want your connection pool to be 8 essentially, or 4 or whatever it is, and then it will actually create new connections to the database until you reach the maximum number of connections, and then it will stop creating new database requests. So on the Postgres end, it doesn't actually know any of this. It just knows that I have incoming requests. It just happens that because you set on your application side, you set your connection pool to 8, for example, Postgres just sees that I only ever get 8 incoming requests, so I only fork myself 8 times.
So this pooling's happening in Rails,
Yes.
right? So it's not anything to do with something like PG Bouncer.
PG Bouncer is also a connection pooler, and I'll go into that just very shortly. So yes, I'll talk about that in just a bit. So but before I get into that,
Rails starts, it makes a pool of say 8 connections, opens all 8 connections to Postgres, which forks for each one, and then it'll just reuse those connections for each database request.
yes, essentially.
Right.
Cool. But yeah, was it T-Mike who asked like that question about the connection pools? Did that kind of answer your question? I mean, I kind of answered it in a very non-technical way, I think, but yeah.
No, that makes sense. I assumed that was a Postgres thing, but if that's happening in Rails to reduce the amount of forked processes in Postgres, that makes a lot more sense.
No, so connection pooling is always a client-side concern. It's never a server-side concern. Yeah, so the Postgres server doesn't care about the connection pooling. It just knows that I have an incoming process. I will fork myself to meet that process. Incoming connection. I will fork myself to meet that connection if I don't have enough. If I don't currently have enough processes to deal with it. So yeah, connection pooling is always client side. Cool. So Mike Lockhart, you asked about PG Bouncer. That's actually what I want to talk about next. So when do we use PG Bouncer? So imagine if you have multiple Rails applications, this would be a scaled scenario. So Rails, and then, of course, each of these Rails, because they're all client-side, they each have their own connection pooler, right? So you end up, instead of like 8 connections, you end up with 24 connections to Postgres, and things start to look bad in terms of performance. This gets even worse the more it goes. So what do we do here? We have PG Bouncer essentially. So PG Bouncer gets rid of all of this. Yep. So we insert PG Bouncer into the, we insert PG Bouncer here. Each Rails connection. This is grossly simplified, by the way. it actually still does a connection pool to PG bouncer, but PG bouncer basically doesn't care about that. And then now basically the connection pool is just between PG bouncer and Postgres. Yes. So this is one of the scenarios in which we need something like PG bouncer, which also serves as a connection pooler in front of a Postgres database.
So what's the difference? Does PG bouncer not fork?
Actually, that's a good question. I don't know the answer to that. I don't think it does. But yeah, I do know that basically instead of having like 5 different connection pools, we use PG bouncer to just have one connection pool serving multiple application clients. There probably is a more technical reason to this, and it's also why I say this is grossly simplified. But yeah, I don't actually know the answer to that one, unfortunately. I mean, since you're on the topic, PG bouncer is not just a connection pooler, of course. PG bouncer, basically, with a PG bouncer, it can actually maintain a list of Postgres servers to connect to. So essentially, if the top one on its list is no longer available, you can go to the next one. And that's the beginnings of a high availability setup for Postgres. But yeah, I won't go into that for this session. Any other questions? Any other questions on connection pooling? Okay. If not, then I do want to cover a few more things about Postgres, not specifically to the service itself, but to more how we use it. So each Postgres server can actually have multiple databases. The one that we use for GitLab is called, if I'm not wrong, Git. That's not a letter G. Is GitLab HQ development, if I'm not sorry, GitLab HQ production. Yes, the database which we use is GitLab HQ production for GitLab. Something interesting to note here, the reason why it's called GitLab HQ production is because I'm guessing when at the very beginning of GitLab, when we created the GitLab Rails application, someone ran this command, Rails new GitLab HQ. Because yeah, this actually is a Rails convention where the database, this is the app name, and then this is the environment that the database is meant to be in. If you actually created a Rails application and run it in your local environment, so a development environment, this would be GitLab GitLab HQ underscore development. You don't see this often, but in some cases, customers do run MetaMost, which is bundled with Omnibus, if I'm not wrong. So sometimes you see MetaMost itself also uses Postgres, so it actually creates a second database in the Postgres server, which is MetaMost production, if I'm not wrong. So one thing to note here is that if I remember correctly, the GitLab rig backup task actually only backs up this database. It doesn't actually back up the MetaMost database, if I'm not wrong. But I could be wrong as well, you know. But yeah, that's always something to look out for. The second thing about this to note is, yes, I'll cover this as well. So what happens in Postgres kind of stays in Postgres. What happens in Rails stays in Rails. So whenever we update a Rails application, we will need to figure out a way to tell the database to update its schema or its data structure in order to meet the needs of the software itself. And that's why we have database migrations. So database migrations essentially are a way for Rails to define, you know, to support this software change. These are the changes I need made to the database. So this is why we have this is why we have database migrations. It's basically a way to keep the database in sync with the changes we make in the application. So yeah, any questions about that? Okay. So the last data store I haven't covered yet is basically the most important one for GitLab, and that is Gitaly, because you know, what would GitLab be without repository storage, right? It wouldn't be called GitLab. It will be called Jira maybe. So yes, Gitaly. Oops. Does anyone know how Gitaly actually works? In terms of, you know, how does Gitaly interact with repositories on the disk?
It forks Git and actually runs Git against its bare repositories on the server.
Yes, exactly. So essentially all Gitaly does is that it takes commands from Rails in terms of in the form of remote procedural calls, and actually runs the raw Git commands on disk against the bundled repositories, or the repositories in bundled form. So yes, you're exactly right.
Oh, sorry. So
No.
it takes gRPC requests and converts them into, say, Git commands, or say Git operations. Is that right?
Yes, that's right. Did you have a follow-up from that?
No. That was my question.
Okay. So yes, that is exactly what it does. So one thing to note here is that Gitaly can't actually run any arbitrary Git commands. It has to run commands based on remote procedural calls, or gRPCs, which have to be predefined by our developers. So yes, Gitaly can't simply run anything it wishes. It can only run what our developers has pre-programmed it to run, I guess, if you can call it that. So excuse me. So essentially, here is how it works, right? So the web Rails or the Sidekiq Rails, I'll just use the web Rails, for example, sends a gRPC. And then Gitaly gets a response. In cases where Gitaly takes too long to get back to Rails, you see that infamous, like, you know, I think it's 14 deadline exceeded. 14 deadline exceeded. This is actually an application error. So there actually are 3 Gitaly timeouts defined with this. There's a fast timeout, there's a medium timeout, and there's a slow timeout. And then there's an overall timeout. The overall timeout, if I'm not wrong, is set to 57 seconds, which is 95% of the Puma timeout. And then the others are set at some value, which I can't remember. So again, this is all designed to prevent a situation where you have a long-running operation that holds up the Puma server from serving more requests. And someone correct me if I'm wrong here. If I remember correctly, the timeout actually happens on the Puma side. So when you see deadline exceeded, it actually happens on Puma. But Gitaly in the background still runs the command. It doesn't care that there's a timeout. It doesn't, you know, do like a queue of the process. It just continues running that Git command until it finishes. So yeah, you occasionally see this in tickets as well, where people ask like, hey, you know, this timeout is happening, but the Gitaly server still seems busy and is still, you know, churning something or other. That's exactly why there's some Git operation that is continuing to run, even though Puma says, you know, I'm done. I don't want to continue with this Gitaly operation anymore.
Sometimes I see in the gRPC requests, it has like a start time, and then it has a deadline start and a deadline end time. So is it that Gitaly's already aware of the deadline that's been set And does it proactively fail if the duration's above that, or does it, as you say, just keep going? But you know, the deadline has already exceeded and already been enforced by Nginx or something.
I'm actually not sure about this one. So to be very transparent, I have not touched tickets on a day-to-day basis for over a year and a half or even 2 years now. So back then that was the case. I'm not sure if this is the case now. So if Gitaly does have a way to kind of like, the deadline has reached and I don't want to operate anymore, then if it actually does that, that's good. And I think that is something that should have been happening. But yeah, long story short, I'm not sure. Sorry?
The gRPC protocol lets clients specify a deadline. And once that's reached, then the request is cancelled. But I'm unclear from what you say whether we actually use that feature in our Gitaly calls. Sounds like we do though.
Because I feel like if that's the case, if there's a the process keep running in Gitaly, there's like inconsistency problems, right? Because Rails doesn't want it to run. Well, stop the process.
Do a big commit and it times out. Yeah, what happens to that commit on the repo?
Right.
Yeah, I'm not sure. I mean, it's just something that I observed. And sometimes I'd see correlations between the deadline and the end time of the operation. But yeah, I don't know for certain if that does happen, but it seemed like it's, I don't know, from observing it, it looked like that was the case, but it'd be good to know if that is the case or not.
Yep, I don't know the answer to this one definitively, so please don't take anything I say as gospel here.
All good. Thank you.
Something else I want to cover with Gitaly is so let's say you have 4 Puma workers available to serve requests, to serve web requests. And say if we want to make a request to view a repository. So with 4 workers, how many concurrent repository requests do you think we can do through Rails?
Is it a trick question? I want to say 4, but
Say a nonsensical number like -3.
okay. Or 8 because there's Puma and Sidekiq. Or is it 2 because there's Puma and Sidekiq?
The actual answer is the intuitive answer is 4, but the actual answer is 2. The reason behind this is that every time a gRPC is made, Gitaly actually sends out a request back to Rails to an internal API. It does this to actually check that the person or the user that is making that request actually has the permissions to view that repository or do that repository action. So in some cases, Gitaly requests can actually occupy up to 2 Puma workers at the same time. For your reference, this API is so API v4 internal allowed. And you might have seen this before in logs as well.
Maybe not lock up 2 workers, maybe 2 threads. Is that better?
Yeah,
Is
I
it
guess.
a thread? Yeah, okay. Just
yeah, 2 threads. I think it's more accurate for Puma. 2 workers would be more accurate for Unicorn. So, but yes, each Gitaly request does take up a bit more. Can take up a bit more threads or workers than you might think it does, because they actually make an internal request before completing the original request. Yeah, so that's one gotcha to know about, which is really handy to know as well, because sometimes customers who have a relatively small omnibus box, a relatively small single box running omnibus can run into things like this where, hey, I'm trying to access a merge request and my colleague is 2 and now suddenly we can't do anything. Yeah, this is why. Although it's been less common now, I think more of our customers are on more beefy machines, but you never know when this is useful to see. The last thing I want to cover with Gitaly is the naming of the gRPCs themselves. So there are two common ones that we see often in logs, and this would be write them down: post, upload, pack, or SSH, depending on whether it's a Git over whether it's Git over HTTP or Git over SSH, and post, receive, pack. So one common mistake I think that people do when they first look at Gitaly logs is they don't realize that the Gitaly logs are actually written from the perspective of the server itself. So post upload pack, if you kind of look at it, you might think that this is actually a Git push, but actually it's a Git pull because it's the Gitaly server uploading data back to the client. And same thing for Git receive pack. You might think that Git receive is like a Git pull because it's the client pulling data from Gitaly, but actually it's a Git push because it's the server receiving data from the client. So this is something else useful to know about as well. Cool. Any other questions? Any questions about Gitaly in general? The last bit to know about for Gitaly is that the main performance driver is always IOPS. Git has many operations that involve many small files. So if you have an IOPS that's really low, like 700, 800 spinning disk essentially, it probably will work, but it'll probably fall over really quickly as well if you have heavy Git operations. You probably want something more in the range of 7,000 to 8,000, which is more like a SSD. So yeah, just something to take note of as well. All right, so that covers all of the internals of the environment, of the GitLab environment. Now we'll talk about how this actually interacts with the outside world. So I'm just going to move this over. So yes, very early on, we talked about reverse proxies, in particular Nginx. So there are actually two main entry points to a GitLab environment. The first one is Nginx. Oops. And the second one is GitLab shell. So both of these are reverse proxies. Reverse proxies are essentially web services or web servers that take a request and then sends them elsewhere, depending on routing rules. Usually this would be hostname and port. So GitLab shell takes on all SSH connections. Generally, we are just sending this, I think, right to Gitaly if I'm not wrong. I could be very wrong, but conceptually, that's what's happened. That's what's happening. Nginx takes all the HTTP requests, and it sends it further along. It also sends it to other places depending on the URL and port. So I won't cover many of these, but essentially this could also send off to places like pages. It could go to our container registry. I don't know the exact port numbers for many of these, but yes, these are some examples of where Nginx can send requests to that's not actually the core GitLab components. But if it does want to send requests to GitLab itself, the core Rails components, it sends it first to GitLab Workhorse. So this is Workhorse. So Workhorse itself is actually another reverse proxy. In most cases, Workhorse will basically send a request over to Rails. But the purpose of Workhorse here, and remember again about the 60-second timeout, Workhorse is there basically to intercept any long-running requests, which we don't necessarily need Rails to actually do. So some examples about this would be handling Git operations over HTTP. We don't need to go through Rails for that. If it's just like, a Git push or whatever it is, I think it just goes to Gitaly itself. So we kind of avoid having to touch the Rails application, which is relatively slow. It also does some other things like, say if you have a runner that wants to upload an artifact. So you'll go to Workhorse. Sorry, it doesn't actually go to Workhorse first. It will go to Nginx. Actually, let me use a different color. It will go to Nginx. It will send it to Workhorse. And then if your artifacts are stored on a object storage, it bypasses Rails entirely, and you just go straight to the object store. This is also the reason why debugging artifacts uploads is notoriously difficult, because all you have to work with are the Workhorse logs, the Nginx logs, the Workhorse logs, and the runner job logs. So yes, you don't get a lot of information there. So hang on, what else? So yes, the whole point of Workhorse here is to basically intercept any request which will probably run longer than 60 seconds or do not actually require the Rails application at all. So this is also an optimization technique. Essentially, don't send requests to the web server if they don't need to be served by the web server. Another common example of a reverse proxy doing this would be using the reverse proxy to actually serve static files instead of going through the web server, and then the web server telling you, please serve this static file. So I don't think we do that with GitLab, or we might, but this is also a common optimization technique that web developers use in other Rails applications. Cool. Oh, in my notes, I do note that GitLab shell actually calls out to the internal API address as well. But yeah, I don't know the specifics of how that works, but it does make sense because you do have to check for permissions as well. So I guess GitLab shell actually does go here for permissions checking. Okay. Yeah, I think that basically covers all the topics I want to talk about with the GitLab Architecture 101. I've covered the internals of it and some of the reasons why we have them that way and how they kind of talk to each other and why they talk to each other that way. I've also covered a bit about basically the front doors through which all requests are served, which is the GitLab shell and Nginx reverse proxies. And purely from a developer's perspective, it's actually very interesting to see how so many of these components are there just to avoid overburdening the Rails application itself, which is, if you read around, people have consistently trashed Rails for being for not being very performant. It's true, which is why we have all of these. So that's it, I guess. So yeah, anyone have any questions or any remarks? We do have about another 10 minutes, I think, for just general discussion.
I have a comment. I think, so it's only on SaaS right now that GitLab shell runs as an SSHD daemon. On self-managed, it still uses OpenSSH. And in the authorized key file, so when you log with SSH using your SSH key, it runs a force command, which then invokes GitLab shell. and then that does all the stuff. So on self-managed, you still log in over OpenSSH first, and then it hits GitLab shell.
You're talking about the recent release of the in GitLab.com using different SSH. I think they're trying.
Yes. So on SaaS right now on GitLab.com, so they are working on replacing OpenSSH, and there's a feature in the new version of GitLab shell where it can actually just run as an SSH daemon.
Yeah, I think that was what Ken brought up last week. That there's a replace. I think it's replacing GitLab.com. It's not yet enabled on self-managed, right?
I don't think we haven't announced it or anything. It might be available in the version of GitLab shell that's in self-managed, but we don't have any documentation or anything about it at the moment. Well, public documentation, I guess.
I remember when I was in my recruitment phase for GitLab and I was reading up on architecture that apparently Workhorse started as a GitLab team member's fun weekend project, but ended up becoming, a critical part of the infrastructure because, yeah, it satisfied a need to, be in front of Rails and Puma and take a lot of the load. I think that's why they called it Workhorse. But yeah, interesting that it just started from, I guess, one person's idea and just, hacking away on the weekend. And now it's where it is now.
One of our other key features, which is GitLab CI, actually started out much the same way. I think back then there was a lot of debate as to, should we have CI as a separate thing or should we, bake it right into GitLab? Camille, I think, was the one that said, you know what, I'm just going to do this. And then it happened the way it did, and it has become quite core to our product.
I'm just sharing a fun read in the document. So having listened to all this, there is a much simpler explanation of how web scaling works, but they explain it in a coffee shop example, which is kind of a bit of a fun read. So if people are interested.
Yeah, I think in many cases, scaling is actually pretty, okay, you know what, maybe it's not, but I think it's quite intuitive. Like, if you want to have multiple application servers because, you have too many incoming web requests, you need two of these, right? And then once you have two of these, you run into the problem of that, having multiple applications hit your Postgres, and then, how do they actually talk to Redis and stuff like that. So it kind of grows from there, but yeah, that's a whole other topic. I think I do have some resources for that as well, specific to GitLab, which I think I'll put in a document, and you can have a look later on if you want. Anyone else have any comments, questions they want to bring up? Otherwise, let's stop this here and we can all go back to the rest of our days.
I do have a question. It's not related to architecture, but the program you're using, is that Microsoft OneNote or a different? Because I've never seen this drawing freehand functionality.
It is Microsoft OneNote. I am actually using a drawing tablet. I'm not sure you can see it. Man, the focus is not working. But yes, I'm actually using a drawing tablet. It's a Wacom. So yeah, you can actually draw. I think you can even draw using the mouse if you want. So I'm using the mouse now. So so yeah, it does work. I actually tried looking for other programs to use with an infinite canvas, but yeah, I couldn't find anything better than OneNote, unfortunately.
We might have to end it there. Wei Ming, you've been summoned by the CEOC for some help in the self-managed channel.
All right. All right then. I mean, we are at time anyway. So thanks everyone for coming. I hope this actually helped you get a better understanding of how the different GitLab components work together. And again, my hope is that you will take this understanding and build out your understanding and also build out our training materials and our documentation so that this doesn't become like the one resource that you use for years on end. I sincerely hope that doesn't happen. So yeah, thanks everyone. I'll stop the recording here. How do I stop the recording?